Where do we want to start today, class? Which one do we want to examine? Which one do we want to examine? Let's use hands today.
16.
Number 16. Which homework is that? 3?
Mr. Seamon?
Yes.
I'm not sure which box I was talking about.
Can someone help him?
Field trip? Okay.
16. So let's clip this in. Biologists have observed that the chirping rate of crickets of a certain species appears to be related to temperature. The table shows the chirping rates for various temperatures. Make a scatter plot, find and graph the regression line. So it's what kind of regression model? Linear. Yeah, linear. And then it says, use the linear model to estimate the chirping rate at 100 degrees Fahrenheit. So what's your specific question about this? Do you want an answer?
Yeah.
Let's have who has a good answer they want to share? Who has an answer they want to share? What's the chirping rate at 100 Fahrenheit? Anybody have an answer to part C? Corey. 264.7. How many people got 264.7 around that? That seems like that seems like you are popular, and that seems reasonable. Does anybody have any specific questions they'd like to see on this? Does that help you?
Yeah.
Okay. Another one that you'd like to see. What? 18. So 18 says, find a model that captures this. So when they say find a model that captures this, what do they mean?
To choose which one.
Choose which one. Yeah, exactly. Choose which one. Is it necessarily, do they tell you which one to try? No. It doesn't happen. So when you do the graph of this, as far as I remember, you end up with something that kind of does this, I think, right? And then you do your line of best fit, not a line. It's definitely not linear, right? Can anybody tell me which model had the best R-squared value? Was with what? Cubic? Did anybody do quartic? Was it better than cubic? I think it was a little better. They're very, very close. They're very close on this. They're very close. And what they mean by diminishing returns is this right here is the percentage increase in efficiency of emissions. And this was the cost. So look what happens. You're getting, you go up 5, you go up 5, you go up 5. It gets better and better, and it's only a nominal cost. But then right here, I think it's at 80% costs $100, I think it is. After that point, what happens? It shoots way up. So if you're looking to make what they mean by diminishing returns is after 80%, you put in the same amount of money, you get less return. You put in another $100, it's only going to get you to here. It's only going to get you to 90%. The first $100 got you to 80. The second $100 gets you all the way to 90. I forget what it is on the chart exactly. But that's what it means by diminishing returns. You put a certain amount of money in and you get less out of it. In this case, it's the efficiency percentage. And do they ask you to predict something on this? I think they ask you just for the formula. Who has a cubic? Who has a cubic that they would like to share? And when you have to round, please round to at least 3 decimal places. Does anybody have the cubic rounded to 3 decimal places on this? Pang, what'd you get? Mm-hmm. Mm-hmm. Yep.
Plus 247.
247, yeah, okay, this is familiar. Yep, 247 what?
675x.
Yep.
Minus 5163. 9.953.
Exactly, very good. So that right there, that matches the cubic we got in the other class. That's fine. Yes.
Could you turn off the...
Oh, I'm sorry. You actually need me to not do that. Okay, I'm sorry. Excuse me. Can you hit the light? So that when they ask you find a model, this would be an acceptable model. You could also do the quartic if you wanted, but that would be acceptable right there. That would be acceptable. Does that help you, Claire, and back? You wanted to talk about this one? No? You got that one? Okay. Okay, are there any other specific ones you want to talk about? Yeah, Corey. 20 what? 20D, yeah. 20D. 20B, you mean? So on this, it says, on this one, how many people have actually worked with Kepler's law before? Anybody? Kepler's law? No one?
Yeah.
Okay, so what we're going to do with this is actually model it. You go up to the one, you press clear, and then you go down, I think it is.
Yeah.
Oh, hold on. You go clear and then down. And you go clear and then down. Yeah, that's how you clear the list. So when it says use a power model, which regression is that? So if I go to stat, calc. Oh, wait, that's not the one I wanted. Stat, calc. Which one should I do? Which one's power?
Down, down.
Power regression. Enter. Right, exactly. And then I do y1. Why do I put that y1 there? It'll put it in. We do this. Okay, let's look at these numbers. Can someone tell me what's really, really interesting about this regression model? What's the most interesting thing by far about this regression model?
Extremely close.
What is extremely close to what?
The R squared. Called.
Yeah, look at that. That is awesome. That means there's probably some sort of direct relationship in play. That's a really, really good relationship. Okay, so now we graph it. Let's go back to here. Let's graph this thing. Does that seem like it models it pretty well? Okay, so everybody, calculators down for a second. Hands up. There we go. So this is our graph right here. That's helpful. So now let's look what this says. It says, I'll copy this down here. It says the square of the period is proportional to the distance. The period was t, and the distance was what? D. If I said A is proportional to B, that means that A is equal to some constant times B. That's what proportional means. How many people have seen that before, proportions? If I said C is proportional to D, that means C is some proportion of K. A common constant to use is K, when you're using K for C for constant. So it says the square of the period. So what's the period? What letter? So the square of the period would be? Is proportional to the distance, the cube of the distance. So D what? And some constant out front, right? Now, what was this model right here? This is power regression, right? Power regression is A times x to the b power. So in this case, it was y equals a. What's a in this case? 1.0005 x to the what power? 1 point what? 49967, right? Let's round this a little bit. What does the coefficient look like it is? 1 times x to the what power? 1.5. And in this case, what is this axis right here? This axis right here was our d, and this was our t. So this was our x value, and this was our... So if we wrote this out, we have t is equal to 1 times d to the... Okay, 1.5 is what fraction? If we want to get rid of fractions, what do we multiply that fraction by to get rid of it? To turn it into a whole number? What do you multiply 3/2 by to make it a whole number? Denominator, which is 2. So if we wanted to keep this having the same value, what power do I raise both sides to? So what do we now have? 2 squared is equal to? So what does that say? What is t again, everybody? The period is equal to the distance cubed. What's the constant in this case? What's the constant in front of d? 1. Period squared, thank you. Period squared is equal to distance cubed. Is that exactly what Kepler's law said? Kepler's law says, read it out loud. The square of the period is proportional to the cube of the mean distance. In this case, what's the coefficient right here in front of d? 1. So it's not written in. But in this case, does this verify Kepler's law? Yeah, it does. The square of the period is equal to the distance cubed. And with that, you're going to lunch. We're going to play a fun game. Real simple. Look at data. What were the world record 1,500 meter women's world record be for speed skating in 2010 based on this data? The one thing I'm going to tell you when you're putting this into your calculator, be really careful about how you input it into your calculator. Be really careful about how you input it into your calculator. Can you use just the year? No. You can't just use the year. Be very careful. Now I start recording. You said cubic regression? Oh, that's pretty good. Cubic regression. Y1. Our R-squared value is 0.9. That's pretty. It's better than mine, right? Now here's the thing. It might be different depending on how you typed in the data, if you made any mistakes. I mean, I've typed it. So now if I predict this though, let's see what this model gives for prediction. So we want to do Y1 at, I entered year 0 was 70 for me, so 2010 is 40. So my answer was this one. Now 2010, I mean, the reason I picked that is maybe the record will get broken. Maybe it was broken last year. Maybe it was, maybe it wasn't, but it might be more interesting to figure out what. We could go check, but we could also, if we wanted to, we could project this farther into the future, maybe. So let's go to 20. Let's make a prediction right now, and 10 years we'll check in on it, right? So if we want to check to see what it is, let's see what it is in 2020. So what's that going to be? Second entry, but 2020. So that's going to be 50 years from 1970. So do we think this is possible? 20 years, so that's, what is that? Yeah, it's going down still. This is 2020. What is that time? That's 1 minute what? 1 minute what? 37.31 seconds. When you're talking about human records, are they always going to go down? No, they're going to probably level off at a certain point. Some records have already. There was big drops 50 years ago. Now they fractionally go down. They could keep on going down, but by smaller and smaller amounts, right? Like if that's the fastest anybody ever is going to go, you get halfway to the wall, halfway to the wall, halfway to the wall, halfway to the wall. You can always get closer to the wall, but are you ever going to get past that wall? No. Okay, what's another? No.
I was only 1 year old. I don't know.
11 months.
11 months.
It was sold out for something like 3 months.
What?
Oh my god.
It was in the theater for 11 months.
I've seen it like 33 hours.
Anyway, it's 3 hours long. Da, da, da. Okay, so we have, ready? We have domestic growth. This is, it is recording. It is recording. Da, da, da. So we have a year here. And this is domestic gross. And don't use 2011. Why?
It's not ended yet.
Yeah, it's only been
So let's stop at 2010. So let's use this data right there. This. Oh, that's pretty cool. Slowed down during the 90s or early 2000s. Seems like it's going back up. Is this something that's going to be able to model too far into the future? Probably not. Probably not. Probably not, but we'll see here. So now if we do the estimate on this one, Y30, let's go by let's do Y30, I guess we can. Do we think the movie industry is going to double its revenue in 10 years? Probably not. So is this cubic super accurate either? Not for that far in the future. But let's do 5-year estimates. If I did a 5-year estimate on my cubic, if I did a 5-year estimate, I'll put in 25. So this is in 2015. Does that look possible? Maybe. Did anybody try a different regression to see if they got something better?
Quarterback.
Was Quartic better?
But the estimates
You can't really go to any model we do isn't going to be very accurate too far in the future. Do you agree? I mean, look, this model right here, the cubic, is it indefinitely going to keep on rising? No, this thing is probably going to not level off, but rise slower.
So like
The quadratic, I think the quadratic makes more sense, but a quadratic goes down. Like we want something that's softer, like the beginning of a quadratic. We want it kind of tapering off a little higher. Another one we could try doing, I'm going to try this. Stat Calc. There's another regression here. I'm going to try Exp Reg Exponential Regression.
What is that?
I'll show you the form. It'll come up. Here's Exp Reg. Now, I have a question for you. Okay, so the R-squared value measures the accuracy of modeling that data, but if you're using this for predictions, R-squared being really good is nice, but this might actually be better than what we've had before. Let's graph this. Here's Exp Reg. Looks a little bit calmer, doesn't it? Let's see what this prediction is. So if we quit out of this and do Y1 at 25. So this is the year 2015. Does that look a little bit more realistic? What do you think?
Yeah.
That looks a little bit more realistic to me. 2025, yeah. Now one other one I want to show you, logistic. There's stat. Let's see if I can find it here. Logistic. Let's see what this looks like. Might take longer for it to actually compute it. So if we try to actually go for this, movie gross, movie top gross inflation. All-time adjusted real ticket price for inflation. See, look at this. Take a look. Gone with the Wind, kids. Gone with the Wind. So Gone with the Wind made $400 million. Look at the year. What year is that? Look at all the other years, everybody. Look at all the other years. Right? So we have this. Gone with the Wind made that much money in 1939. So what do we need to know if we want? So again, what was our conclusion here? Gone with the Wind would have made $6 billion domestically. Nice. Your homework's going to be to find and analyze at least 2 interesting data sets. Find and analyze at least 2 interesting data sets. You find them. Get out of here.